Hey Royals, in today's lesson, we're going to look at accelerated motion. So before we get too far into it, let's discuss what the heck acceleration actually is. And for this, I want you to imagine that you're sitting in a car and the light in front of you is red. So you're stationary, but as soon as it turns green, your foot goes to the gas and the car starts to speed up. This change in speed or change in velocity is referred to as acceleration. And while we're on the same concept, I want to think about you driving down the highway and you see some stop traffic in front of you. You go ahead and put your foot on the brake of your car and you start to slow down. This is also known as acceleration. Commonly, people refer to this as deceleration, but in fact, in the world of physics, there is no such thing as deceleration. It just simply is acceleration in the negative direction, or backwards. And we'll discuss what I mean by this at the end of today's lesson. So, for this lesson, we need to identify the fact that we are going to be looking at position time graphs, velocity time graphs, and acceleration time graphs. And before, in an earlier lesson, we looked at how the slope of a position time graph gave us the velocity of the object. Now the same is true for the slope of a velocity time graph, giving us the acceleration of the object. So what I mean by that is if you think about the slope equation, y2 minus y1 divided by x2 minus x1, it looks a lot like this equation here that I defined as acceleration. So what we're going to do is we're going to start with some position time information. We'll plot it on a graph, and I've already done that for us here. And I'm going to then calculate the slope of this line and determine the velocity. Now, how do I know that this car or this object is actually speeding up just from the data? And in fact, this is a cart rolling down a ramp. So if I look at my data, I know it's accelerating because the gap between adjacent values is getting larger. So the gap between these two is 2, whereas the gap between these two is 19. So that's telling me that my object must be speeding up. So I'm going to say the cart is speeding up since the steps between position points is getting bigger. Okay, now I've already graphed my data here, so I would encourage you pause the video here, get your data graphed, and then come on back. All right, so now that you've graphed it, we have to determine the slope of this. And you're looking at the graph and going, this is a curve. It's not straight. How do I determine the slope of a curved line? Well, in fact, we can't actually calculate it as we did in a previous class. We need to introduce this idea of a tangent. Now, because the slope is positive and it's increasing, that suggests to us that the velocity is also increasing. Because if we remember, the slope is the velocity. If I look at this, I notice that the steepness of my red lines is increasing as I move from left to right. Now, what I'm going to do is I'm going to use a line similar to what I've just drawn there, and that's called a tangent line. The tangent line will only touch the graph at one point, and it will have the same slope as the point that it's touching the graph at. So I'm going to go ahead and I'm going to draw a tangent line that touches exactly at 5 seconds. That needs to be a little steeper. So it's going to be difficult because you're not going to get it exactly right because we are humans, not computers. Even though I'm using a computer to do this, I'm still not going to get it perfect. Now, I think that's pretty good for a tangent line at 5. So it's matching the slope right here, and it's only touching exactly at 5 seconds. So if I can calculate the slope of that red line, that gives me the slope of our black position data at 5 seconds. So I'm going to go ahead and calculate the average velocity at this position right here. Or sorry, I'm going to calculate the slope of my line here. And that will be, we need our data off of our line here. So this will be at 7 and 45. And then 4 and, I don't know what that looks like, 15. And I'm picking data that crosses right at a grid mark. So I'm using those 2 points there. So that will be 45 meters. We're going from start. Okay, so we're going to be 45 meters from the start minus 15 meters from the start. And the difference in my time is 7 seconds minus 4 seconds. If I go ahead and calculate that, I get that it's 30 meters in 3 seconds, which gives me 10 meters per second. So the slope of my tangent line at 10 seconds, at 5 seconds is 10 meters a second. Now I'm going to encourage you to pause the video, draw some tangent lines on your graph, and I want you to determine the tangent of the curve at 1 second, 3 seconds, 7 seconds, and 9 seconds. Okay, so once you've done that, come on back to the video and we'll continue on from there. So welcome back. I've drawn a series of tangent lines on my graph and I've calculated the slope of each of these lines. And I've listed them here in my velocity versus time data table. Okay, so what the next thing I want to do is I want to determine the velocity of the object or this cart rolling down the ramp as a function of time. Okay, so I'm going to take my data here and I'm going to put it onto my graph, and I encourage you to do the same for the data that you came up with. If it's not the same as mine, that's totally fine. Now I've graphed my data here and I've put a line of best fit. So what I want to do is I want to calculate the slope of this line of best fit. So if I calculate this slope of it, I'm actually calculating the acceleration of the object. So my acceleration of my object will be v2 minus v1 divided by t2 minus t1. And if I look at my data here, I'm going to choose this point right here is 2 and 4. And I'm also going to choose the point 6 and 12. Okay, so those will be my 2 points that I'm using. So 12 meters a second forward, I guess. I'll use FWD minus 4 meters a second forward divided by 6 seconds minus 2 seconds. If I calculate this out, I get that I have 8 meters a second forward divided by 4 seconds. And that 4 doesn't quite look right, so 4. And I get that it's 2 meters a second squared forward. So I know that my acceleration of this object is 2 meters a second squared forward. Now what we can actually do with this is we can discuss what will be happening to the object. So for constant acceleration, and this is constant acceleration because my velocity is a straight line, the graph can actually tell you a lot about the object. So if I'm getting a positive slope here, I'm having the object accelerate forward, which means, or I say in the direction of motion. So it's accelerating in the direction of motion. If the slope is negative, I'm accelerating, I'm going to say backwards, or in the opposite direction. Opposite direction to motion. And if the slope is 0 on my velocity time graph, that means the velocity is not changing, which means no acceleration. In that case, we have it and we know it as uniform motion. Okay, so what I want to do is I can actually go backwards, just like we did in our uniform motion lesson. We can go backwards from our velocity time graph to our position time graph. And it's done by calculating the area under the curve. So we can actually calculate the area under the curve, and let's do it at 5 seconds. So from t equals 0 to t equals 5 seconds, we'll put a seconds there, I want to calculate the area under the curve. So I want to find out the area that is underneath this curve, so the pink triangle that I've just made here. So let's figure out the area of that triangle. So the area is going to be 1/2 the base times the height. So 1/2 the base of this is 5 seconds. The height of this is 10 meters a second, and we can say, I guess, forward. And if I calculate this out, 10 times 5 is 50, half of 50 is 25. Meters times seconds, divide by seconds, I get meters, and that's forward. It tells me that therefore, at t equals 5 seconds, the object's displacement should be 25 meters forward. Now let's see how that compares to the data that was given to us in the question. So if we compare that to the data that was given to me in the question, at 5 seconds, it should be roughly 25. And that's exactly what we got. It was 25 meters down the ramp. So I calculated here that it was roughly 25 meters forward. What should the displacement be? So I'm going to say from data table for position. The cart moved 25 meters down the ramp. And I'm going to put a smiley face here because that's actually pretty impressive that we got the exact same answer. Now, I don't expect you to get the exact same answer because, of course, your tangent lines were drawn completely by humans, not by a computer here. Okay, so what can we actually do? Well, I can calculate or use this acceleration to make an acceleration versus time graph. So if I'm looking at the slope of this line, the slope will never change. My acceleration will always be 2 meters a second squared forward, which means that my acceleration time graph should be always 2 meters a second squared forward. Okay, and we can actually go ahead and calculate the velocity at a given point. So again, just like we did before with the area under the curve, it allows us to go back one step with our graphing. So if I calculate the area under the curve for the first 5 seconds, so from t equals 0 seconds to t equals 5 seconds, I get that the area is length multiplied by the width. So the length here is 5 seconds. The width was 2 meters per second squared, and that we can say is forward. And if I multiply these together, I get 10 meters a second forward. And again, this should match up with what we had before. So at 5 seconds, the velocity, so therefore the velocity at 10 seconds should be 10 meters a second forward based on our area under the curve calculation. And if I go back to my graph here, at 5 seconds, if I go up and across, sure enough, I get 10 meters a second forward or down the ramp. So that's pretty impressive that we're matching up exactly with the step before. Now, if we think about the acceleration being constant, that means that something is going to change with the velocity. The velocity is going to either increase or decrease. I'm assuming that the acceleration is not constantly zero. And then the position time graph will have a characteristic shape. And so let's discuss what we mean by that, and so that we have all the shapes kind of summarized in one place. So if I assume that the right direction is positive, and I have acceleration in the right direction and the velocity in the right direction, that means that the ball, in this case, is already moving towards the right, and the acceleration is also to the right. So what's actually happening? It's going to accelerate in the direction of motion. So what does that mean? It's going to speed up. So the position that I cover every second is going to increase because I'm actually speeding up. So my shape of my graph will do something like this. And if we think about our tangents, the tangent line to my curve is actually getting steeper and steeper and steeper, which means that the velocity is getting larger and larger and larger as I move through time. Now, if the velocity is moving towards the right, so positive, and the acceleration is negative, that means that the object must be slowing down. So it is accelerating, accelerates opposite to direction of motion, which means that it's slowing down. Okay, so if I'm slowing down, initially I'm going to be moving very quickly. So initially I'm going to be moving very quickly, and then my velocity is going to get lower and lower. So my graph should start very steep and start to decrease. So the velocity, the tangent to this line, should get its slope being lower and lower and lower and lower. Okay, so that would be what the characteristic image of a position time graph would look like. Now let's flip the whole situation. Let's say that the velocity is in the negative direction, and the acceleration is in the negative direction, which means I have the object accelerates in the direction of motion. In this case, negative. Okay, so it's moving in left. So my graph is towards the right, so my displacement should be a negative because it's moving to the left. Now it's getting faster and faster and faster in the left. So initially, let's assume it's going very slow, and then it gets faster. So the steepness of my line gets larger, and then it gets faster. So the steepness of my line gets even steeper. So if I connect these, I get that my curve is going downwards. Okay, so that is characteristic of the acceleration and the velocity both being in the negative direction. Okay, so the last one here, I have that the velocity is negative and the acceleration is positive, which means that it accelerates opposite to direction of motion. And in this case, again, if these are in opposite directions, it's slowing down, which means the steepness of my line gets shallower and shallower. So I start out with a line that is very steep in the negative direction. It's going fast in the negative direction, but it's getting less and less steep. So the shape would be something like that. Okay, so in this lesson, we looked at how I can determine the velocity from a curve that is not necessarily straight. So I used a tangent line. I also then discussed how we can use a velocity time graph to get the acceleration. and we looked at the characteristic shapes of position time graphs for objects that are experiencing acceleration. Okay, so again, if you have any questions, please reach out to me and ask some questions.